You're watching Bite-Size Revision here on BBC Learning Zone, and tonight's subject is GCSE Maths, and we continue with number and measures.
Hello and welcome to GCSE Bite-Size. This programme will help you with your GCSE Maths exams. It focuses on what you need to know about numbers and measures. There are other programmes about algebra and shape, space and data handling. The best way to revise with Bite-Size is to tackle one topic at a time, working through the video in bite-sized chunks. Each programme is full of useful information with sample questions for you to try. And there's more in the GCSE Bite-Size books and on the GCSE Bite-Size website at www.bbc.co.uk/revision. There are many different exam boards, but their questions are similar. Maths papers are set at 3 different levels or tiers. If you do the foundation level paper, you can get grades G to D. If you do the intermediate paper, you can get grades E to B, and the higher tier paper covers grades C to A star. Your teacher should have discussed with you which paper is best for you to go in for. During the programme, watch out for the icons which show the levels we're dealing with. This programme on number and measures is divided into numbers and the number system, calculation, calculation skills, and measures and construction. First, numbers and the number system. This section is divided into the counting numbers, quotients, irrationals, and extending the notation. First, the counting numbers. Natural numbers are the whole numbers that we count with, like 1, 2, 26, 203, 476,678, and so on. Integers are the positive and negative whole numbers, like minus 348, minus 6, 0, plus 7, and so on. All natural numbers and integers are made up of one or more digits. For example, 348 is made up of the digits 3, 4, and 8. This digit is a 7, but 7 what? Let's put a marker in. Then add a heading for hundreds, tens, and units. Now we can see that 7 really means 700, and the marker is a decimal point. We know that 7 stands for 700 because it's in the hundreds column, but we need to be certain there's nothing in the other columns. The Babylonians first had the idea of showing there's nothing there by putting in zeros. We can now read this as 700s in the third column, nothing in the second column, and nothing in the first column. That's 700s, no tens, and no units. 700. The number system we use is based on the Hindu Arabic system, which uses only 10 different symbols or digits, 0 to 9. These 10 digits make all the numbers we need. The secret of its success is the idea of place value. If a digit is in a different place, it's a different number. The digit 7 placed here means 7. Here it means 70, and here it means 700, and so on. Think of a petrol pump or car distance counter. As the numbers start counting, when 10 is reached, a 1 appears in the next window because we've clocked up 110. When we clock up 10 tens, a 1 appears in the next window because we've clocked up 100, and so it goes on. So the place value system is based on 10. Each column, hundreds, tens and units, is actually headed according to powers of 10. 1 is 10 to the power 0, 10 is 10 to the power 1, 100 is 10 to the power 2, 1,000 is 10 to the power 3, 10,000 is 10 to the power 4, 100,000 is 10 to the power 5, and 1,000,000 is 10 to the power 6, and so on. There's more about powers in the section on extending the notation. When doing written calculations, it's vital to get the place value of individual digits right. A digit in the wrong place means a completely different number. For example, in this multiplication, this 2 really means 2 tens. It's the 20 part of 23. So the answer starts in the tens column with 20 times 1, that's 20. There is nothing in the units column, so nothing is written there. In fact, we write a 0 to show there's nothing there. Place values based on powers of 10 don't stop with units. The system continues with negative powers, representing fractions. So 1/10 is 0.1 or 10 to the power minus 1. 100th is 0.01 or 10 to the power minus 2. 1000th is 0.001 or 10 to the power minus 3, and so on. Decimal fractions are based on tenths, hundredths, and so on. For example, 0.25 is the same as 2 tenths and 5 hundredths, which is 25 hundredths. If you simplify the fraction, it's the same as 1/4. That's the end of the section on the counting numbers. Next, quotients. Quotients are either fractions, decimals, or percentages. First, fractions. Fractions like 1/2, 4/9, or 15/26 are called division fractions because they represent a division. 1 divided by 2, 4 divided by 9, 15 divided by 26. Different fractions with the same values are known as equivalent fractions. For example, if a sandwich is cut into 2 parts and you have one of those 2 parts, then you get half a sandwich. If you have a sandwich cut into 4 parts and you have 2 of those parts, then you still get half a sandwich. If the sandwich is cut into 8 parts and you've had 4 of those parts, then again you've had half a sandwich. We can represent this mathematically by saying that a half is equivalent to 2 quarters, is equivalent to 4 eighths, is equivalent to 8 sixteenths, and so on. The bottom numbers are doubling from 2 to 4 to 8 to 16, and the top numbers are doubling from 1 to 2 to 4 to 8, and so on. So fractions are equivalent when their top and bottom numbers, their numerator and denominator, are in the same proportion. In this case, the bottom number is always twice the top number. We can do the same with 1/3, 2 sixths, 3 ninths, and 4 twelfths. Here the proportion is the same because the bottom number is always 3 times the top number, so all the fractions in this series are equivalent. If the exam says express a fraction in its lowest form, it means to find the fraction that's at the beginning of the equivalent series. For example, to find the lowest form of 10/30ths, work back to the start of the reducing pattern of equivalent fractions, 9/27ths, 8/24ths, 7/21ths, and so on, until you reach a third. In each fraction, the bottom number is 3 times the top number. The quick way to get the lowest form of 10/30ths is to divide both the 10 and the 30 by 10. This gives 1/3, 1/3, so the lowest form of 10/30ths is a third. The value of the fraction has not been changed, but the top and bottom numbers have been made as small as possible. What is the lowest form of the fraction 42/49? To simplify this fraction to its lowest form, we're looking for a number that will divide into both the top and bottom parts of the fraction. 7 goes into 42 6 times, and into 49 7 times. So the lowest form of 42/49 is 6/7. Here's another one. What is the lowest form of the fraction 48/54ths? To simplify this fraction to its lowest form, we're looking for a number that will divide into both the top and bottom parts of the fraction. This can be done in more than one step. We can see that 48 and 54 both end in an even digit, so they can both be divided by 2. That makes the fraction 24/27ths. But we can go further. Both 24 and 27 can be divided by 3, and that makes the fraction 8/9ths, which is as far as we can go. So the lowest form of the fraction 48/54ths is 8/9ths. Of course, you could have simplified this in one go by dividing the top and bottom by 6. So the quickest way to simplify a fraction to its lowest equivalent form is to divide the top and bottom parts of the fraction by the same number. Choose a number that will reduce the top and bottom numbers of the fraction to their smallest possible value. This keeps the same proportion between the top and bottom numbers of the fraction, and so the value of the fraction is the same. Now on to decimals. Decimals are another way of writing fractions. You should know these decimal and fraction equivalents. A half is equivalent to 0.5, a quarter, 0.25, 3/4, 0.75, a tenth, 0.1, a fifth, 0.2, and 3/10, 0.3. You can find the decimal equivalent of a fraction by doing the division suggested by the fraction. So 1/4 is 1 divided by 4, which is 0.25. Many fractions have an exact decimal equivalent, but many do not, and must stay written as a division fraction to be accurate, as well as easier to handle. For example, 1/3 as a decimal is 0.333 recurring, and a sixth is 0.161616 recurring. A seventh is even more awkward. It's 0.142587 recurring. And a ninth is 0.1111 recurring. It's useful to remember these. To turn a recurring decimal, like 0.333 recurring, into its equivalent fraction, there's a handy method. Let x be the fraction we're looking for, equivalent to 0.333 recurring. Multiply both sides by 10 to give 10x equals 3.333 recurring. This makes the first recurring 3 a whole number. Now subtract one equation from the other. To give 10x subtract x, that's 9x equals 3.3 recurring, subtract 0.3 recurring, that's 3. That's got rid of the infinite string of decimal 3's and left 9x equals 3. So x, the equivalent fraction we're looking for, is 3/9, or 1/3. What is the equivalent fraction of 0.090909 recurring? Now, you may already know this, but let's work it out anyway. Let x be the fraction we're looking for, equivalent to 0.09 recurring. Multiply both sides by 100 to give 100x equals 9.09 recurring. Subtract one equation from the other to give 100x subtract x. That leaves us with 99x equals 9. That's got rid of the infinite string of decimal 0/9's. So x, the equivalent fraction we're looking for, is 9/99. That's 1/11. To summarise, fractions are written as divisions. Fractions with the same value are equivalent to each other. Many fractions can be simplified to their lowest equivalent form. Some fractions have exact decimal equivalents. Some fractions have recurring decimal equivalents and are easier to use if they are kept in their division form. Next, percentages. This next clip explains what they are.
Most of the numbers we come across in day-to-day life describe actual amounts or quantities. 2 metres of cloth, 3 handkerchiefs, 25 pence in change and so on. And if I change the amount, I change the number. There, now it's 50 pence. But percentages, proportions and ratios are ways of sharing things out. Percent means parts in 100. 1% means 1 part in 100. 6% means 6 parts out of 100, and so on. So a percentage is a fraction of 100. 100% of anything is the whole lot. So if one sock is 100% pure wool, a pair of the same socks is also 100% pure wool, even though I now have twice the amount of wool. If I imagine something divided into 100 parts, then the number in front of the percent sign tells me how many parts of the 100 I'll get as my share. The best way to start thinking about percentages is as pennies in the pound. So, with 100 pennies in a pound, 10% is 10 parts of the 100, or 10 pence. 50% is 50 pence, and 100% is 100 pence, the whole lot. Now, if a sale sign says there's 10% off the marked prices, then on something marked £1, I would save 10 pence. On something marked £2, I would save 2 lots of 10 pence, that's 20 pence. And on something marked £3, I'd save 30 pence. The actual amount I save varies, 10, 20, 30 pence, but the saving is still 10% of the original price.
So percent means parts out of 100, and 100% means the whole lot. Here are some common percentages with their equivalent fractions. You should know these so you can use them quickly to calculate percentages in the exam. For example, to find 25% of £2, you can say that 25% is 1/4 of £2, which is 50 pence. To find 39% of £423, we know that 39% is 39 hundredths of £423. So multiply 423 by 39 and divide by 100 to get the answer, £164.97. That's the end of the section on quotients. Next, for intermediate and higher, irrationals. Integers, fractions and decimals are called rational numbers, but some numbers can't be represented exactly and completely as an integer, a division fraction or a decimal. These are called irrational numbers. They're usually represented by symbols. One example of an irrational number is pi, which is written using the Greek letter p. Another irrational number is the square root of 2. Pi is the ratio of the circumference of a circle to its diameter. It's used a lot in mathematics. We can't write pi as a rational number, so we approximate its value or use the symbol. Pi is 3.14159, etc. This number goes on forever. It's not a recurring decimal, and it can't be converted into an exact division fraction. We usually say that pi is approximately 3.142, or as a fraction, 22/7. The square root of 2 is another irrational number. It's approximately 1.414, or more accurately, it's 1.4142136, etc. This number goes on forever. It's not a recurring decimal, and it can't be converted into a division fraction. In fact, most square roots are irrational, like root 2, root 3, root 5, root 6, and so on. Those that are not irrational are the roots of square integers, like root 4, which is 2, or root 25, which is 5. Most cube roots are irrational as well, except for the cube roots of cubed integers, like cube root of 8 or cube root of 27. At the higher tier only, you might be asked to simplify an irrational square root, such as the square root of 12. We can turn the 12 into 3 times 4, so root 12 equals root 3 times 4, which is the same as root 3 times root 4. Now we know the square root of 4 is 2, so we can rewrite the square root of 12 as 2 times root 3. Let's simplify the square root of 50. We're looking for a factor of 50 that has a rational square root. Try 25. So root 50 is root of 2 times 25, which is the same as root 2 times root 25. We know the square root of 25 is exactly 5, so we can rewrite root 50 as 5 times root 2. This method can help us simplify expressions like root 63 over root 45. Root 63 is root 9 times 7, and root 45 is root 9 times 5. So we have the square root of 9 on the top and bottom of the fraction, so we can cancel them out, leaving root 7 over root 5. That's the end of the section on irrational numbers. Next, for intermediate and higher, extending the notation. This section is about powers and indices, and the standard form of notation. First, powers and indices. We know that a plus a plus a is the same as 3 times a, which we write as 3a. Multiplication is repeated addition. The prefix 3 shows us how many a's we've added. But what about repeated multiplication? There's a different notation for this. A times a times a is written with a small index number 3 just after and above it. The index number 3 shows us how many a's are being multiplied. We say this is a to the power 3. So a times a times a times a 4 times is a to the power 4. And a times a times a times a times a 5 times is a to the power 5, and so on. Applying this to some simple integers, 2 to the power 3 is 2 times 2 times 2 equals 8. 6 to the power 4 is 6 times 6 times 6 times 6 equals 1296. 10 to the power 6 is 10 times 10 times 10 times 10 times 10 times 10, 6 times, which is 1 million. There's a way of multiplying different powers of the same number together. What is a to the power 5 multiplied by a to the power 3? To see what's happening, write out each power of a as a repeated multiplication. A to the power 5 is 5a's multiplied, and a to the power 3 is another 3a's multiplied. That's 8a's multiplied altogether. That's the same as a to the power 8. So a to the power 5 multiplied by a to the power 3 is a to the power 5 plus 3, that's 8. So to multiply powers of the same number, you add the index numbers together. What about dividing powers of the same number? What is a to the power 5 divided by a to the power 3? To see what's happening, write out each power of a as a repeated multiplication. Cancelling the fraction leaves a times a, which is a to the power 2. So a to the power 5 divided by a to the power 3 is a to the power 5 subtract 3, that's a to the power 2. So to divide powers of the same number, you subtract the index numbers. So a to the power m times a to the power n equals a to the power m plus n, and a to the power m divided by a to the power n equals a to the power m minus n. Now, what happens if n is larger than m? What is a to the power 3 divided by a to the power 5? This is a division, so subtracting the index numbers gives a to the power 3 subtract 5, that's negative 2. This is correct, but what does a negative index number actually mean? Let's write out a to the power 3 divided by a to the power 5 as a repeated multiplication. This gives a fraction that cancels down to 1 over a times a, or 1 over a squared. So a to the power negative 2 is the same as 1 over a to the power 2. The effect of a negative power is to create a reciprocal. In general, a to the negative power n is 1 over a to the power n. Does this system of power notation include fractions? What is 3 to the power 1/2? The fractional index number is the 1/2, but what does 3 to the power 1/2 actually mean? If we multiply 3 to the power half by 3 to the power half, according to the multiplying powers rule, we get 3 to the power half plus a half, that's 3 to the power 1, or plain 3. But the only number that multiplied by itself equals 3 is the square root of 3, so 3 to the power half must be the square root of 3. Let's check out 3 to the power 1/3. If we cube 3 to the power 1/3, we get 3 to the power 1/3 plus 1/3 plus 1/3. That's 3 to the power 1, or plain 3. So as before, 3 to the power 1/3 equals the cube root of 3. So in general, a to the power 1 over n is the same as the nth root of a. Now for powers of powers, what is 4 to the power 3 raised again to the power 2? If we write the power 2 as repeated multiplication, we get 4 to the power 3 times 4 to the power 3. That's 4 times 4 times 4 times 4 times 4 times 4, or 6 4s multiplied together, which is 4 to the power 6. The effect is to multiply the index numbers. So 4 to the power 3 to the power 2 is the same as 4 to the power 3 times 2, which is 4 to the power 6. This also works with fractional powers. What is 4 to the power 2 to the power 1/3? The multiplication rule gives 4 to the power 2 times 1/3, which is 4 to the power 2/3. Using what we already know about powers, this is the same as the cubed root of 4 squared. Next, the standard form of notation. Very large numbers like this and very small numbers like this can be difficult to handle. Standard form is a shorthand way of writing very big or very small numbers. It also makes them easier to understand and to manipulate. Standard form makes use of place value and powers of 10. Take the large number 14,529,000 with its place value headings. We can remove those zeros by moving the number 3 places to the right, but to compensate we need to multiply the shortened number by 1,000. That's 10 to the power 3. Equally, we can move the number 1 more place to the right to make 1,452.9 times 10 to the power 4, and so on. If we want our number to start in the units column, we compensate by multiplying it by 10 to the power 7. So the original number, 14,529,000, can be written as 1.4529 times 10 to the power 7. This is known as standard form. The number part is made to fall between 1 and 10, and is compensated by being multiplied by a power of 10. Now, let's take this very small number, 0.0000429,763. To turn it into standard form, we want the number to start in the units column. We do this by moving the digits 5 places to the left. Then we compensate by dividing by 100,000. That's the same as multiplying by 10 to the power minus 5. So our original very small number is written in standard form as 4.29763 times 10 to the power minus 5. Convert these numbers into standard form. 267, 4,130, 60,000 and 7,600,000. To convert these numbers into standard form, their number part needs to fall between 1 and 10, compensated by being multiplied by a power of 10. 267 is 2.67 times 100, which is 2.67 times 10 to the power 2. 4,130 is 4.13 times 1,000, which is 4.13 times 10 to the power 3. 60,000 is 6 times 10,000, which is 6 times 10 to the power 4. 7,600,000 is 7.6 times 1 million, or 7.6 times 10 to the power 6. It's easier to multiply or divide very large or very small numbers when they're in standard form. The standard form number parts are easier to handle, and the powers of 10 follow the rules for powers. Here's an example. Multiply 430,000 by 32,000. This isn't too difficult as it is, but without a calculator we could get into a tangle with all those zeros. So first, convert the numbers to their standard form. That gives 4.3 times 10 to the power 5, multiplied by 3.2 times 10 to the power 4. Multiplying 10 to the power 5 by 10 to the power 4 gives 10 to the power 5 plus 4. That's 9, and the 4.3 and the 3.2 multiply to 13.76. 13.76 times 10 to the power 9 in proper standard form is 1.376 times 10 to the power 10. Here's a more difficult one that really relies on standard form to work out. Multiply 4,300 million by 0.7032. As well as having lots of zeros to deal with, this might even be too many digits for a calculator to handle. So first, convert the numbers to their standard form. That gives 4.3 times 10 to the power 9, multiplied by 3.2 times 10 to the power minus 8. Rearrange the multiplication to group the powers of 10 together. Multiplying 10 to the power 9 by 10 to the power minus 8 gives 10 to the power 9 minus 8, that's 10 to the power 1, which is plain 10. The 4.3 and the 3.2 multiply to 13.76. So the answer is 13.76 times 10, or 137.6, or 1.376 times 10 to the power 2 in standard form. That's the end of the section on numbers and the number system. This section is about calculation. It covers arithmetic, arithmetic with integers, and arithmetic with quotients. Some of this may seem obvious, but it's easy to get wrong answers in the exam by not doing calculations accurately. So first, we'll look at some arithmetic. This section looks at the principles and methods of addition, subtraction, and multiplication. First, addition. Addition is the grouping of quantities. In its simplest form, it is counting on, such as along a number line. 3 add 4 means starting at 3 on the number line and counting on 1, 2, 3, 4, and you arrive at 7. So 3 add 4 equals 7. To speed things up, you should know your number bonds. That's what pairs of numbers add up to. You should certainly know the result of adding pairs of single digits up to 10, such as 3 add 5 is 8, or 5 add 6 is 11, or 7 add 9 is 16, and so on. This saves working them out each time. For two-digit numbers, jotting down the addition on a rough number line is still a useful method. To add 27 to 48, first add 20 to get to 68, and then add the 7 to reach 75. So 48 add 27 is 75. What is 356 add 4,789? You could still use a number line, But another way is to break the numbers into units, tens, hundreds and so on. Then add the units, tens and hundreds separately, jotting down the results of each addition. So there are 4 thousands, 300 and 700 make another 1,000, 50 and 80 add up to 130, and 6 and 9 are 15. Adding the subtotals gives the answer, 5,145. Some people find it easier to lay out the numbers in columns. As before, add the units, the tens, the hundreds and so on separately. The units 6 and 9 add up to 15, the tens 50 and 80 add up to 130, the hundreds 300 and 700 add up to 1,000, and there's another 4,000. Adding the subtotals gives the answer 5,145 as before. This is not quite the same as the formal written addition method involving carrying. That comes next. The two numbers are lined up in their columns of units, tens, hundreds and so on. Adding the units 6 and 9 gives 15, which is written with the 5 in the units column and 110 carried over into the tens column. Then, when adding the tens, 5 and 8, add in the carried 10 to give 14 tens. Again, the 4 is written in the tens column and the 100 carried over into the hundreds column. There it's added in with the 3 and 7 hundreds to give 11 hundreds. 1 is written in the hundreds column and 1,000 carried over into the thousands to be added to the 4,000 to give 5,000. That gives the answer 5,145 as before. This carrying method is popular, but it's easy to make mistakes by forgetting to add in the carried ones. Next, subtraction. In its simplest form, subtraction is counting back along a number line. 3 subtract 4 means starting at 3 on the number line and counting back 1, 2, 3, 4, and you arrive at -1. So 3 subtract 4 equals -1. As with addition, knowing the number bonds for numbers up to 10 will allow you to do many simple subtractions in your head without working them out each time, such as 8 subtract 5 is 3, 11 subtract 6 equals 5, or 16 subtract 9 is 7. For 2-digit numbers, jotting down the subtraction on a rough number line is still a useful method. To do 75 subtract 48, start at 75 and first count back 40 to reach 35 and then 8 to reach 27. So 75 subtract 48 equals 27. As with addition, larger numbers like 4,356 subtract 789 can be broken down into their units, tens and hundreds, and each part dealt with separately, jotting down the result of each subtraction and looking out for negative numbers. So there are 4 thousands, 300 subtract 700 is -400, 50 subtract 80 is -30, and 6 subtract 9 is -3. Working down the subtotals gives 4,000, subtract 400 is 3,600, subtract 30 is 3,570, subtract 3 is 3,567, which is the answer. Alternatively, you can use a formal pencil and paper method to work out subtraction, again keeping a clear idea of place value. As with addition, the two numbers are lined up in their columns of units, tens, hundreds and so on. With this method of subtraction, you have to avoid negative digits, but there's a way around this. Looking at the units, 6 subtract 9 is -3. We can't have negative digits in the final answer, so we have to adjust the top number to avoid getting them. If we reduce the 5 tens in the tens column by 10 to become 4 tens, and increase the number in the units column by 10 to become 16 units, we can subtract 9 to get 7, no negative numbers. Moving along to look at the tens column, we now have 4 tens subtract 8 tens, which will give -4, so we have to make another adjustment to the top number to avoid this. This time, reduce the 3 in the hundreds column to 2 and give 100 to the tens column to give 14 tens. Now we can take 8 from 14 to get 6 tens in the answer. The hundreds have the same problem. 2 subtract 7 would be -5, so the top number has to be rearranged again. The 4 in the thousands column is reduced to 3 and 1000 given to the hundreds column to make 12 hundreds. We can take 7 hundreds from 12 hundreds to give 5 hundreds in the answer. So we are then left with the 3000s, so the answer is 3567. This can be a messy process, and you have to be sure that you're reorganising the top number correctly and not losing bits on the way. A useful check for any subtraction is to add the answer to the second number to see whether they add up to the first number. We can see that our check shows that we have the correct answer. Next, multiplication. Multiplication is repeated addition. 2 multiplied by 4 is 2 added together 4 times. 37 times 48 is 37 added together 48 times. This would take a long time, so multiplication is a quick way of doing it. Knowing your number bonds, better known as your times tables, for single-digit numbers up to 10, will allow you to do many multiplications in your head without working them out each time. Such as 8 times 5 equals 40, 6 times 4 equals 24, or 7 times 9 equals 63. For two-digit numbers like 37 times 48, there are several techniques that break the numbers down into their units and tens. 37 is 30, that's 3 tens, and 7 units, and 48 is 40, 4 tens and 8 units. Every part of one number has to be multiplied by every part of the other number. Here are 2 ways of doing this. One way is to set out the multiplication in a grid, with the 30 and 7 across the top, and the 40 and 8 down the side. Then complete the grid by multiplying each pair of numbers. 40 times 30 is 1200, 40 times 7 is 280, 8 times 30 is 240, and 8 times 7 is 56. Add the numbers in each cell to give the answer, 1776. For large numbers, like 467 multiplied by 625, the grid still works, though it will be bigger to accommodate the extra place values, and you need to make sure you get the right number of zeros. A second way of multiplying 37 by 48 is to put the numbers in columns with their units and tens lined up. As with the grid, you multiply each part of one number with each part of the other. 40 times 7 is 280, 40 times 30 is 1200, 8 times 7 is 56, 8 times 30 is 240. Add up these subtotals to get the answer, 1776. This is not quite the familiar long multiplication involving carrying. That comes next. In this method, we multiply the 37 by the 40 and the 8 in turn. 40 times 7 is 280. Write down the 80 in the tens column and park the 200 in the hundreds column. 40 times 30 is 1200, plus the 200s already parked there gives 1400. Next, multiply the 37 by the 8. 8 times 7 is 56, so we write the 6 in the units and park the 50 in the tens column. 8 times 30 is 240, plus the 50 already parked there gives 290. The final step is to add the subtotals to get the answer, 1776. To multiply by powers of 10, use your understanding of place value. To multiply 345 by 10, the hundreds become thousands, the tens become hundreds, and the units become tens. The digits move to the left by 1 column. They all increase by 1 power of 10. Multiplying a number by 100 moves all the digits 2 places to the left. They all increase by 2 powers of 10, and so on for 1000, etc. This also works for decimal fractions. What is 0.083 multiplied by 100? This is the same as multiplying by 10 to power 2, so moving all the digits 2 places to the left suggests the answer is 8.3. Some calculations are mixed operations, a mixture of adding, subtracting and multiplying, and there's a correct way to write them down and a correct order to do them in. 30 plus 4 times 3 is a confusing expression because it's not clear which operation should be done first, the addition or the multiplication, and it makes a big difference. 30 plus 4 is 34, times 3 is 102. On the other hand, doing 4 times 3 first gives 12. Add the 30 gives 42. To make clear what's intended, this expression should have brackets round the bit that should be done first, either round the 30 add 4 or round the 4 times 3. Then there's no confusion over what the answer should be. Over the years, mathematicians have agreed that operations should be carried out in a particular order. Brackets, indices, multiplication, division, addition, subtraction. You can remember this from the acronym BIMDAS. So, in our example, if there were no brackets shown, the correct way is to do the multiplication first. That's 4 times 3, 12. Then add the 30 to give 42. All counting numbers are either prime numbers or unique products of other prime numbers. Prime numbers that combine to make another number are called factors. Prime numbers can only be divided by themselves and 1. 1 is not a prime number because it only has one factor and not 2. This list shows how numbers are either primes or the product of primes. That is, they have factors that are primes. We can use factors to help with multiplying fractions, like 6/16 times 4/15. 6 and 16 share a factor of 2. 6 and 15 share a factor of 3. 4 and 16 share a factor of 2. This is the principle behind cross-cancelling fraction multiplications. 3 goes into 6 and 15. 4 goes into 4 and 16. And 2 goes into 2 and 4. To give a half times a fifth, that's a tenth. That's the end of the section on arithmetic. Next, arithmetic with integers. It's easy to make mistakes with the positive and negative signs for numbers. The problem arises because plus and minus are used to mean two different things. The direction of a number, positive or negative, or the operation performed on a number, addition or subtraction. The first meaning, the direction of a number, tells us where the number is on the number line. Positive 3 and negative 3 are different numbers in different positions on the number line. They are in fact 6 numbers apart. The second meaning refers to the operations. Plus means addition and minus means subtraction. When these two uses are combined, the trouble starts. Here we have the number positive 3 added to the number positive 2. The plus signs are used in the two different ways, the green signs for direction and the red signs for the operation. A number line will give the answer for this. Start at positive 3 and count on for addition by positive 2. That takes us on two numbers to positive 5. So adding a positive number is the same as simple addition. A plus and a plus together act like a plus. Here we have the number positive 3 added to the number negative 2. Again, a number line will give the answer. Start at positive 3 and count on by negative 2. That takes us back two numbers to positive 1. So adding a negative number is the same as subtracting that number. A plus and a minus together act like a minus. Let's look at when the operation is subtraction. We have positive 3 subtract positive 2. On the number line, starting at positive 3 and counting back for subtraction, by positive 2 gets us to positive 1. So subtracting a positive number is just the same as subtraction. A minus and a plus together act like a minus. Here we have positive 3 subtract negative 2. On the number line, starting at positive 3 and counting back for subtraction by negative 2 gets us to positive 5. So subtracting a negative number is the same as addition. A minus and a minus together act like a plus. So here are some rules. If the signs are the same, it's addition. If the signs are different, it's subtraction. What happens when the operation is multiplication? Here, a positive number times a positive number gives a positive answer, and a positive number times a negative number gives a negative answer. Remember, multiplication is repeated addition, so 3 negative 2's are negative 6. Similarly, when multiplying a negative number by a positive number, the answer is negative, and a negative times a negative is a positive. So again, if the signs are the same, the answer is positive. If the signs are different, the answer is negative. These are the rules for division. Again, if the signs are the same, the answer is positive. If the signs are different, the answer is negative. That's the end of the section on arithmetic with integers. Next, arithmetic with quotients. Quotients involve division and can be fractions, decimals, percentages, or ratios and proportion. First, let's look at arithmetic with fractions. Fractions don't follow the same rules as whole numbers because they already include a division. 4/7 is already 4 divided by 7, and we write it as the fraction 4 over 7. We can also describe 4/7 as the number of parts a whole is divided into. This whole is divided into 7 parts, and we have 4 of them. When adding fractions, we can't just add sevenths and thirds. We have to make them be the same denominations. We do this by finding a common number that we can convert each denominator, 7 and 3, into. To do this, we look at the multiples of each. We can see that the first multiple which both 7 and 3 share is 21. So the lowest common multiple is 21. We can now convert our existing denominators into the new common denominator, 21. To turn a seventh into 21sts, we multiply top and bottom by 3 to get 3 21sts. To turn 1/3 into 21sts, we multiply top and bottom by 7 to get 7 21sts. Our addition is now 3 21sts plus 7 21sts, which is 10 21sts. In practice, a quick way to get a common multiple is to multiply the two denominators together. That's 3 times 7, 21. A general rule for the addition of fractions is a over b plus c over d equals a times d plus b times c over b times d. Similarly, to do 3/4 subtract 7/10, we again need to find the lowest common multiple of the two denominators, 4 and 10, which is 20. We can now convert the two denominators to the new common denominator, 20. To turn 3/4 into 20ths, multiply top and bottom by 5 to get 15 20ths, and to turn 7/10 into 20ths, multiply top and bottom by 2 to get 14 20ths. This gives both fractions the same denominator, 20, which we can now subtract, and 15 20ths subtract 14 20ths is 1 20th. A general rule for the subtraction of fractions is a over b subtract c over d equals a times d subtract b times c over b times d. What is 2/3 multiplied by 4/7? When multiplying fractions, we don't need to find common denominators. Think of a square that measures 1 unit on each side and mark off 2/3 of a unit on one side and 4/7 of a unit on the other. The shaded area will be 4/7 multiplied by 2/3. But the whole square has 21 parts, and the shaded area has 8 parts. That means that the area of the shaded portion is 8 21sts of the whole. So 2/3 times 4/7 is 8 21sts. Now this answer is what you get by multiplying the top numbers of the fraction together, 2 times 4, and multiplying the bottom numbers of the fractions together, 3 times 7. And this is how we multiply fractions. Notice that when you multiply a fraction by a fraction, the answer's smaller than what you started with. So in general, the multiplication of two fractions, a over b times c over d, is a times c over b times d. Next, dividing by a fraction. 2 divided by a half the number of halves in 2 is 4. 3 divided by 1/4, the number of quarters in 3 equals 12. You might notice that the answer to 2 divided by a half is the same as 2 times 2, and the answer to 3 divided by 1/4 is the same as 3 times 4. So when dividing by a fraction, the effect is the same as turning the fraction upside down and multiplying. So 40 divided by 4/9 is the same as 40 multiplied by 9/4, which simplifies to 10 times 9, that's 90. Again, notice that when you divide by a fraction, the answer is bigger than the number you started with. It's the same if we divide a fraction by a fraction, like 2/3 divided by 3/7. This is equivalent to 2/3 multiplied by 7/3. That's 2 times 7, 14, over 3 times 3, 9, or 1 5/9. So in general, dividing A over B by C over D gives A times D over B times C. Next, doing arithmetic with decimals. When multiplying decimals, we have to be careful about the size of the answer. For example, what is 0.2 times 0.2? If we think of the 0.2 as a fraction, it's 2/10. Multiplying 2/10 by 2/10 equals 4/100. 4/100 as a decimal is 0.04. So multiplying 0.2 by 0.2 is 0.04. We can check this by using the area model again. Take a unit square and mark off 0.2 on 2 sides. Here we can see that the shaded area of the square, 0.2 by 0.2, is only 4 squares out of the whole 100 squares. This confirms that 0.2 times 0.2 is 4/100. That's 0.04. Again, notice when you multiply a decimal fraction by a decimal fraction, you get an answer smaller than the numbers you start with. When you divide a fraction by a fraction, the answer is bigger than the numbers you started with. What's 0.3 divided by 0.14? Converting this to fractions gives us 3/10 divided by 14/100. To divide by a fraction, turn it upside down and multiply. So that's 3/10 times 100 over 14. That's 3 times 100, 300, over 10 times 14, 140, which simplifies to 30 over 14, or 15 over 7, which is 2 7, or, as a decimal, 2.142857 recurring. Next, doing arithmetic with percentages. This clip is about Jessica Miller, who makes scarves, and the percentages she has to deal with.
Working out what to charge for a product is one of the most important calculations a designer will make. So when Jessica Miller is pricing her hand-painted scarves, she can't afford to make a mistake. Jessica makes these exclusive accessories by hand-dyeing and painting plain silk scarves before selling them to shops and galleries around the country. Like a lot of young designers, she has to live on a very tight budget and needs to keep a firm control over production costs. And working out how much profit she can make isn't just a case of quoting the first price that comes into her head.
If you charge too little for your work, people feel that it's worthless, that you must be using bad materials. If you charge too much for your work, no one will pay for it.
So how do you work out the price?
Well, start with the cost of the raw materials. So let's see, say somebody wanted to buy a scarf from me. One scarf would cost me to buy, the blank scarf, £2.70. But if I buy 12, the price comes down to £2.50 each. So I would actually buy 12.
So what percentage saving does Jessica make by buying 12 scarves at once rather than one at a time? The saving Jessica makes is the difference between the cost of buying a scarf singly, £2.70, and in bulk, £2.50. That's 20 pence. As a percentage, that's the 20 pence saving divided by the higher price, £2.70, and multiplied by 100 to give a percentage. That's 7.41%. To turn the plain white scarves she buys into the beautiful coloured ones she makes, Jessica has other costs. There's the cost of the dyes and their own time, and the other costs like telephone, postage and electricity bills.
So Jessica's costs are £40 a day for 2 days. That's £80. Now add that to the cost of the materials, and that makes it £120 for the 12 scarves. Divide that by 12 and it's £10 each. But that's still not the price that Jessica charges the shop.
I would also like to make some profit on top of that. So I think £4 profit per scarf seems reasonable, so I would charge £14 for a scarf.
So what percentage profit does Jessica make on her scarves if they cost £10 each to make and she sells them for £14? The profit is the difference between the selling price, £14, and the cost of making them, £10. That's £4. As a percentage, that's the £4 profit divided by the cost price, £10, multiplied by 100, or 40%. Now, Jessica has to add value-added tax, VAT, at 17.5% to the £14 sale price. How much is the VAT on one scarf? Although 17.5% seems a tricky figure, you can work it out without a calculator. First, work out 10% of £14, that's 1/10 or £1.40. 5% is half of 10%, that's 70 pence. 2.5% is half of 5%, that's 35 pence. Adding all these together gives 17.5% of £14 is £2.45. Next, arithmetic involving ratio and proportion. This clip is about the different scale models the architects made of London's Canary Wharf office block.
In an architectural model, every dimension, height, length and breadth is reduced equally. Everything remains in scale. All the angles remain the same. The tower is 260 by 58 by 58 metres. The model is 1:500, so its dimensions are 52 by 11.6 by 11.6 centimetres. Each dimension 500 times less. However, models of Canary Wharf are built in a variety of scales. While smaller scale models are able to show large areas effectively, they have little detail. So, a 1 to 3000 scale model, that's every dimension 3000 times smaller than real life, will show the development in the context of the wider landscape, presenting much of London but virtually no detail. In the 1 to 500, we start to see windows, individual trees, and the shape of buildings exact to form. 1 to 100 is the most common presentation model because it shows all the necessary architectural details, even the individual bricks and textures of the construction materials.
If a 1 to 100 scale were used, what would be the model's height, length and width in centimetres if the real height is 260 metres and the base is 58 metres square? In a 1 to 100 scale model, each dimension will be 100 times smaller than the real building, so the height will be 2.6 metres and the base 0.58 metres square. Or in centimetres, 260 centimetres high, with a base 58 centimetres square. That's the end of the section on calculations. We now move on to look at calculation skills. This section covers mental methods, written methods, calculator methods, and takes a look at estimation. First, some tips for doing mental arithmetic. Don't always reach for your calculator. You should be able to add numbers quickly in your head. That's mental addition. The first tip is that it's easier to add a small number to a large number. And don't forget that with addition, you can always change the order of the numbers you're dealing with. So what's 37 add 86? To add 37 and 86 in your head, first change it to 86 add 37. Then break down the 37 into 30 and 7. 86 add 30 is 116. Add the 7 makes 123. The next tip is that numbers near to tens can be rounded up or down to the nearest 10. Then you adjust the answer to compensate for the rounding. So what's 74 add 48? You can round up the 48 by adding 2 to make the sum 74 add 50, which is easy to do. That's 124. Then adjust the answer by subtracting the 2 you added to make 122. It's often easier to add large numbers by starting with the largest value first. Then break each number into its hundreds, tens and units and add each separately. So to add 345 and 672, put the large number first and then break the numbers into their hundreds, tens and units. First, add the hundreds, 600 and 300, that's 900. Then, add the tens, 70 and 40, that's 110. Finally, add the units, 2 and 5 is 7. This gives a total of 1017. It may not be possible to do this completely in your head, but you can jot down the subtotals. Mental subtraction uses some of the same techniques. Work from the larger number, break the numbers down into hundreds, tens and units and deal with them separately. Round up or down to the nearest 10 and adjust the answer. But remember, unlike with addition, the order of the numbers in a subtraction does matter. People who play darts are usually good at mental subtraction. You start the game with 501 and take away each score you make until you end up at 0. If your opening score is 2 20s and a 5, your new score would be 501 subtract 45. You can round the 501 down to 500 and take away 40 to get 460. Then take away the remaining 5 to get 455. Then add back the 1 to compensate for the rounding to get the answer, 456. If your net score is 137, you'll be left with 456 subtract 137. Let's turn this subtraction into an addition. 456 subtract 137 is like asking, what do I add to 137 to make 456? To do this, count on from 137 to 456 along a number line. From 137 to 140 is 3, on to 440 is another 300, and finally on to 456 is 16. Adding up the steps, that's 300 add 16, 316, add 3 is 319. So the difference between 456 and 137 is 319. If you're multiplying by a single digit number, there are some easy to remember methods. To multiply by 10, you move the digits one place to the left. To multiply by 5, you multiply by 10 and halve the answer. So 84 times 5 is 840 halved, that's 420. Multiplying by 2 is doubling. Multiplying by 4 is doubling twice, and multiplying by 8 is doubling 3 times. So 56 times 4 is 56 doubled once, that's 112, doubled again equals 224. 43 times 8 is 43 doubled, that's 86. Doubled again, 172. Doubled again, 344. Other single-digit multiplications can be based on multiplying by 2, 5 or 10. To multiply a number by 3, double it and add the number once. So 36 times 3 is 36 doubled, 72. Plus 36 makes 108. To multiply a number by 6, multiply the number by 5, that's by 10 halved, and add the number once. So 42 times 6 is 42 times 10 halved, plus another 42. That's 210 add 42, 252. To multiply a number by 7, multiply the number by 5 and add twice the number. So 23 times 7 is 230 halved, 115, plus twice 23, which is 115 add 46, 161. To multiply a number by 9, multiply the number by 10 and take away the number once. So 68 times 9 is 68 times 10, 680. Subtract 68 gives 612. So here's a summary of these mental methods for multiplying by single-digit numbers. If you're dealing with two-digit numbers, you need to break them up into tens and units and multiply each part separately. You'll probably need a pencil and paper to keep track of what you're doing in your head. So when multiplying 23 by 38, there are 4 parts to deal with. The 20 and the 30 and the 3 and the 8, and each part has to be multiplied separately. So 20 times 30 is 600, 20 times 8 is 160, 3 times 30 is 90, and 3 times 8 is 24. Add all the parts up, 600, 160, 90 and 24, to get the answer 874. If you use this method, you may need to jot down the subtotals as you go. Remember, as with addition, the order of the numbers in a multiplication doesn't matter. For division, you can use the opposite of the multiplication rules, but unlike multiplication, the order of the numbers does make a difference to a division calculation. So dividing by 2 is halving, by 4 is halving twice, and by 8 is halving 3 times. Also, dividing by 5 is the same as doubling, then dividing by 10. So 112 divided by 8 is half of 112, that's 56. Halved again, that's 28, and halved again to give the answer 14. 235 divided by 5 is 235 doubled, 470, divided by 10, which is 47. That's the end of the section on mental methods. Next, written methods. If you can't do a calculation in your head, the method you can use depends on whether you're doing the calculator paper or the non-calculator paper. In any event, you do need to be able to add, subtract, multiply and divide without a calculator. So here's a quick summary. When doing written addition, make sure you line up the columns correctly. Here, 8 add 4 makes 12, put down the 2, carry 1 10. 20 add 50 makes 70, plus the carried 10 makes 80. 700 add 300 makes 10 hundreds, put down the 0 and carry 1000. 1000 add 1000 makes 2000, to give the answer 2082. It doesn't matter where you put the carried numbers, but whatever you do, don't forget to include them in the calculation. This is written subtraction. Again, make sure the columns are lined up correctly. 2 take away 7 you can't do, so borrow 10 from the 50 leaving 40 and give it to the 2 to make 12. 12 take away 7 is 5. 40 take away 60 you can't do, so borrow 100 from the 400 leaving 300 and give it to the 40 to make 140. 140 take away 60 is 80. Finally, 300 take away 200 is 100, answer 185. There are several methods for written multiplication, which all involve multiplying each part of one number by each part of the other number. To multiply 78 by 43 by the column method, you can start with the units or the tens. The answer will be the same. Let's start by multiplying the 78 by 40. First, put down a 0 for the 40. 40 times 80 is 320, so put down the 20, carry the 300s. 40 times 70 is 2800s, add the carried 300 makes 3100s. Next, multiply the 78 by the 3, 3 times 8 is 24, put down the 4, carry the 20. 3 times 70 is 210, add the 20 makes 230, and add up the subtotals. This gives the answer, 3,354. A second method is to use a grid to set out the 43 as 40 and 3, and the 78 as 70 and 8, and then multiply the four parts separately. 70 times 40 is 2,800. 70 times 3 is 210. 8 times 40 is 320, and 8 times 3 is 24. Then you add up all the subtotals to get the answer. That's 3,354 again. Another method is an ancient Indian method that uses a slightly different grid of squares with diagonal lines. Put in the 78 and the 43. Now fill in the boxes, like this. 4 sevens are 28, 4 eights are 32, 3 sevens are 21, 3 eights are 24. Now add up the diagonals starting from the right. The first diagonal has just 4, so put down the 4. The next diagonal has 2 add 2 add 1 makes 5. The next diagonal has 3 add 8 add 2 makes 13. Put down the 3, carry a 1. The final diagonal has 2 and the carried 1 makes 3. So there's the answer, 3,354. Finally, here's a way to do written division. What's 510 divided by 12? First, how many 12s are there in 51? That's 4, because 4 12s are 48, with 3 left over, so carry 3. Next, how many 12s in 30? That's 2. 2 12s are 24, with 6 left over. This means we have to put down a decimal point, so we write 0.0 and carry the 6. Finally, how many 12s in 60? 5. Put a decimal point in the answer as well, to give the final answer, 42.5. That's the end of the section on written methods. Next, calculator methods. There are questions on the calculator paper that expect you to use a calculator, even if you could work them out using written methods. A calculator will always give you some answer, but if it's been used wrongly, it'll be the wrong answer. You also need to know how to use the features on your scientific calculator. First, we have the trigonometry keys, sine, cos and tan, and above them the inverse trig keys, which you get by using the shift key. Then there's the power key, to the power of, and above it the root key. We also have separate keys for square and square root. Also there's a key for the reciprocal, and above it the factorial. Finally, we have a key to enter negative numbers. And, most important, 2 keys for entering brackets. There's also a special key to enter a value for pi. 2 more tips. Use the calculator's bracket keys to help with complex calculations. And if you need to write down parts of the calculation, write it to more decimal places than you'll need in the answer, so the calculation doesn't lose accuracy as you work through it. This is the sort of calculation you might be asked to do in the exam. If you start off left to right keying in 5 plus square root of 3 plus 4 and so on, you'll get the wrong answer. You have a go at doing this correctly on your scientific calculator. To do this properly, you need to put brackets around the parts of the expression that need to be held together. The square root sign written over more than one number acts like a bracket. The long division line means the top and bottom expressions should be in brackets. Finally, put brackets around the whole fraction to separate it from the 5. So let's use our scientific calculator and see what we come up with. Now the brackets are all in place, we can enter each step of the calculation carefully in that order, using the bracket keys and using the division sign for the fraction line. So we should enter 5, add, open bracket, square root, open bracket, 3 plus 4, close bracket, times 17, close bracket, divided by, open bracket, 32 to the power 2, subtract 1020, close bracket, equals, which gives 16.2444307. But we're asked to give the answer to 2 decimal places, so that's 16.24. That's the end of the section on using the calculator. Next, for foundation and intermediate, estimation. There is often a question on the non-calculator paper that asks you to estimate the value of a calculation. It's important to know what the examiner is looking for here. They don't want you to work it out accurately and then invent an approximate answer. They want you to round all of the numbers to the simplest they can go and then work out the answer. You must show in your workings that you've done this. So let's estimate the answer to 41.7 times 28 divided by 4.896. First, write each number as simply as we can. Round 41.7 down to 40, round 28 up to 30, and for 4.896 put 5. Now we can work it out. 40 times 30 divided by 5, that's 1200 divided by 5, that's 240, which is the answer the examiner is looking for. Even when doing complicated calculator questions, it's useful to do an estimate to check what you've done on your calculator. In this section, we've looked at some hints for doing mental calculations, methods for doing written calculations, some tips on using a calculator, and a brief look at estimation. That's the end of the section on calculation skills. This section is about measures and construction. It covers measures, construction, and mensuration. First, measures. Here, we'll look at bearings and then a bit about measuring lengths. First, bearings. This clip explains.
We all know there are 4 main compass points: north, east, south and west, each pointing in a different direction and separated by a right angle. There are also directions such as northeast and southwest, which fall in between the main points. Now, these terms are not accurate enough to allow an aircraft to navigate from one place to another, so they use bearings, breaking the compass points into 360 degrees. East is 90 degrees, south 180, west 270, and north is 0 or 360 degrees. So planes can fly on a bearing of, say, 148 degrees or 330 degrees, which is far more accurate than the compass points. Where should we go? Barbados?
Why not?
Good idea. Now then, let's see. We take off on runway 26 and stay on a heading of 260 degrees to Land's End. Then change heading to 225 degrees and head out across the Atlantic. We'll do the next leg on a heading of 228, change course to a heading of 238, another change to 226 degrees, and make our final approach to Barbados on 210 degrees.
A lighthouse keeper notices a yacht in distress out at sea on a bearing of 340 degrees, about 7 nautical miles from the lighthouse. Fortunately, there's a rescue ship on a bearing of 60 degrees, also about 7 nautical miles from the lighthouse. Using 1 centimetre to represent 1 nautical mile, draw the positions of the yacht and the ship, and work out how far and in what direction the ship will need to travel in to rescue the yacht. First, let's do the drawing. Position the lighthouse and then position the yacht on a bearing of 340 degrees, measuring from north at the lighthouse and placing it 7 nautical miles, that's 7 centimetres away. Then, position the ship on a bearing of 60 degrees, measuring from north at the lighthouse, placing it 7 nautical miles, 7 centimetres away. Now to work out the answer. Join the position of the rescue ship to the position of the yacht and measure the distance between them. It's about 9 centimetres, so the ship is about 9 nautical miles away from the yacht. To find the direction the ship needs to travel, we need the bearing of the yacht from the ship. If you want the bearing from the ship, this means starting from the ship. Imagine facing north and measure the angle from north round to this line joining the ship to the yacht. This angle is about 290 degrees. So the answer is that the ship must travel 9 nautical miles on a bearing of 290 degrees to reach the yacht. Note that when giving bearings, you don't need to include degrees, as this is assumed. So we can write 290 and not 290 degrees. Next, measuring lengths. This short section is about units of length and degrees of accuracy. This next clip explains.
Take this bar. Imagine we needed to use it as part of an accurate factory process. How long would you say it was? Well, we can say that its length is between 3 and 4 meters. To the nearest meter, we'd say it was 3 meters long. Suppose we now subdivide 1 meter into tenths. To the nearest tenth of a meter, it's 3.2 meters, but it's really 3.1 something. More subdivisions. About 3.16 meters. That's to the nearest hundredth of a meter or centimeter. To the nearest millimeter, the length is 3.164. We could go into more detail, but the important point is when we've reached a level of precision good enough for the job.
So, when giving an answer in meters, notice that 3 decimal places is to the nearest millimetre and 2 decimal places is to the nearest centimetre. That's the end of the section on measures. Next, construction. To the ancient Greeks, a centrepiece of mathematics was what you could create with a pair of compasses and a straight edge. It's something your examiners are interested in as well. First, you need a good pair of compasses. The best type has the pencil built in, but if you have to fit the pencil, make sure it's tightly fitted and doesn't get in the way. It's best to have your own pair. When we draw in this way with a pair of compasses and a ruler, it's called construction. If you're asked to construct something in the exam, you must show that you have used the compasses properly. The telltale signs to the examiner are little construction arcs on your page. In this section we're going to create 3 constructions: a triangle, a perpendicular bisector which divides a line exactly in 2 with a line at right angles to it, and an angle bisector which divides an angle exactly in 2. First, constructing a triangle. To construct a triangle with sides 7 cm, 5 cm and 6 cm, first draw a line 7 cm long. Now set your compasses to 6 cm on your ruler. Place the point at one end of the line and draw a short arc. Now set the compasses to 5 cm. Place the point at the other end of the line and draw an arc that crosses the first one. Use your ruler to join up the triangle. Check that the 2 lines are 5 cm and 6 cm. You should practice drawing lots of different triangles. For the exam, they should be accurate to within 1 mm or you will lose marks. Next, constructing a perpendicular bisector. We're going to draw the perpendicular bisector of this line, which will be halfway along and at right angles to it. First, set your compasses to a little more than half the length of the line. Put the point on one end of the line and draw 2 small arcs, one on each side of the line. Now put the point of your compasses into the other end of the line and draw 2 more arcs crossing the first ones. Now accurately join up the crosses. You can check with your ruler that the base has been divided into 2 exactly equal parts. Also, check that the new line is at right angles to the base. Next, constructing an angle bisector. An angle bisector divides an angle exactly in half. Set your compasses a few centimetres apart. It doesn't matter how much, as long as it's not too big that it goes off the page, nor too small to be fiddly. Then place your compass point at the point of the angle you want to bisect and draw arcs cutting the 2 sidelines. Now place your compass on one of the new crossing points and draw another arc in the middle of the angle. Then do the same from the other crossing point. Finally, draw a line joining the point of the angle to the new crossing point. This bisects the angle. You can check this with your angle measurer. So, in this section, you've seen how to construct a triangle, a perpendicular bisector and an angle bisector. Don't forget you must show your construction marks or you will lose marks in the exam. That's the end of the section on construction. Next, mensuration. This section looks at formulae for triangles and rectangles, the area and circumference of circles, the volumes of solids, using volume and surface area formulae, and something about dimensional analysis. First, formulae for triangles and rectangles. The area of a rectangle is its length times its width. That's A equals L times W. A equals LW. The area of a square is also its length times its width. But as both these are the same length, that's the same as the square of one of its sides. That's A equals L times L. That's L squared. The area of a triangle is 1/2 its base times its height. That's A equals 1/2 B times H. The area of a parallelogram is its base times its height. A equals B times H. Remember, before you start to calculate an area, make sure both the dimensions are in the same units, all centimetres, metres or kilometres, etc. If not, you must change one to match the other. If, for example, one dimension is in metres and the other is in centimetres. And don't forget to show what units your answer's in, like centimetres squared or metres squared, etc. You'll lose don't. Next, for intermediate and higher, the area and circumference of circles. The radius of a circle is the distance from its centre to its outside edge. The diameter of a circle is the distance right across a circle through its centre. So the diameter of a circle is twice its radius, that's d equals 2r. The circumference of a circle is the distance all the way around its edge. The ratio between the circumference and the diameter of a circle is constant at just over 3. That constant is called pi, written using the Greek letter p. So we can say that for any circle, its circumference divided by its diameter equals pi. That's c over d equals pi. Another way of putting that is to say that the circumference of a circle is pi times the diameter, c equals pi d. Since the diameter is twice the radius, we can also say that the circumference c equals pi times 2r, or c equals 2 pi r. There's another formula for the area of a circle. Imagine dividing a circle into many small sectors, then rearrange those sectors into a rough rectangular shape. The smaller the sectors, the closer to a rectangle the shape will be. To improve the rectangle shape, half of this end sector needs to go at the other end. We can see that the long side of the rectangle shape is half the circumference of the original circle, pi times r, and the short side is the same as the radius, r. So the area is pi times r times r. So the formula for the area of the circle is A equals pi times r, which we write as A equals pi r squared. This is a really important formula to remember. So, altogether, we've got the circumference of a circle C equals pi d, or 2 pi r, and the area of a circle A equals pi r squared. Remember that the units for the circumference of a circle should be units of length, and the units for the area of a circle should be units of area. Next, we'll look at sections of a circle. An arc is part of the circumference of a circle. A sector is a slice of a circle made up of 2 radii and an arc. In the exam, you might be asked to calculate the length of an arc or the area of a sector of a circle. To work out either of these, we need to know the sector angle that the arc or the sector contains. This angle is a fraction of the whole circle, which is 360 degrees, so we can work out the fraction of the circle we are dealing with. The arc length is the same fraction of the total circumference of the circle, and the area of the sector is the same fraction of the total area of the circle. For example, if the sector angle is 90 degrees, then the sector is 90 degrees out of a total of 360 degrees, that's a quarter of the circle. And the arc length will be a quarter of the total circumference of the circle, and the area of the sector will be a quarter of the area of the whole circle. What is the arc length and area of a sector with angle 38 degrees in a circle of radius 8 centimetres to 2 decimal places? Before we can work out the length and area of the arc, we need to work out the length of the whole circumference and the whole area of the circle. Now we know from our formula that the circumference C equals 2 pi r and area A equals pi r squared, where r is the length of the radius of the circle. When you do calculations with pi, you can use its approximate value, 3.142, or the pi button on your calculator. So the whole circumference is 2 times pi, 3.142, times the radius, 8. That's 50.272 centimetres. The area of the whole circle is pi, 3.142, times 8 squared, 64, which is 201.088 centimetres squared. At this stage, keep your answer more accurate than you'll need. Okay, If the sector angle is 38 degrees, then the length of the arc will be 38 360ths of the whole circumference. That's 38 over 360 times 50.272, that's 5.30648, which is 5.31 centimetres to 2 decimal places. The area of the sector is 38 360ths of the whole area. That's 38 360ths of 201.088, which is 21.22585, or 21.23 centimetres squared to 2 decimal places. Next, the volumes of solids. A cuboid is a three-dimensional solid whose faces are all rectangles. The volume of a cuboid is the area of its base multiplied by its height. And for a rectangular base, the area equals the length times width. A equals L times W. So the volume of a cuboid is length times width times height. V equals L times W times H. You can use the formula volume equals the area of the base times the height to calculate the volume of other solids with uniform cross sections. A cylinder has a circular base with an area pi r squared. So the volume V equals the area of the base times the height. That's pi r squared times H. In a similar way, the volume of a triangular prism can be worked out by using the formula volume equals the area of the triangular base times the length. Remember, volume is measured in cubic units, so always give your answers in cubic centimetres or cubic metres, etc. A sphere is one more solid shape we need to look at. There are two useful formulae that go with it. The surface area of a sphere is 4 pi r squared, where r is the radius of the sphere. And the volume of a sphere is 4/3 pi r cubed, where r is the radius of the sphere. Next, using volume and surface area formulae. This section will give you practice in using the formulae for the area and volume of spheres, cubes and cylinders. Here's a clip about why the design and shape of a balloon is important.
So what components do you need to make a hot air balloon? And how do you enable it to fly?
You need to have a certain amount of hot air. You need a basket to carry the passengers, and you need a burner to create the hot air, and you need a fuel storage, which are your cylinders. And these are the components that make a balloon.
With cold air inside, a balloon would just lie on the ground. But a balloon flies on the principle that hot air rises. When air is heated, it expands, making it thinner and lighter. This process creates a lifting force, so the balloon rises. If enough hot air is trapped inside the balloon, it can lift quite a heavy basket. Manufacturing hot air balloons is an art as well as a science. And of course, there's also the mathematics. Designing novelty balloons like these is a mathematical challenge, and the Thunder and Colt team are experts at it. Most of these special shapes do not hold a large volume of air, which means they're inefficient and can carry only a very small load. The problem is that the ratio between surface area and volume is poor. In other words, they use a lot of heavy material, but do not hold a lot of air.
Let's have a look at the Pacific Flyer. I'll rotate it for you.
Pear's team used computer-aided design to build the Pacific Flyer. They now use the computer to design all their balloons, which makes it much easier to do the sums and quicker.
We can see that in section here.
Good.
This view of the Pacific Flyer was used to calculate how large the circumference would need to be at its widest point.
The size of a balloon would depend on the weight it has to carry and how long it has to fly. In our case, we need to fly for 3 days, which meant about 6 tons of propane had to be carried. And with that, you can calculate the volume, and that came out as 2.6 million cubic foot. That is about 75,000 cubic meters. And just the air inside the balloon weighs about 75 tons. It is very big. In fact, you can fit a jumbo jet inside the balloon itself. The computer is a very fast calculator. It's not intelligent as such, but it can calculate obviously 1 million times faster than the man can. So once we define the volume, we tell that to the computer. It will then draw up the shape, calculate the surface area, and eventually divide it into panels down to the actual patterns we use for cutting and stitching the balloon up, and load that down to the cutting machine, and it will optimize the use of the fabric, so we have as minimum waste as possible. And in fact, we can design this balloon from the screen direct to cut fabric without seeing paper.
So let's investigate the best shape for a balloon. To save material and therefore weight, the best shape for a balloon is one that has the smallest surface area for the same volume. Let's suppose that to support the weight of its load, the volume of a balloon must be 3,000 cubic meters. Which shape has the smallest surface area that can contain this volume? Is it a sphere, a cube, or a cylinder that's as high as it's wide? To answer this question, we'll need to work out the surface area of each shape from the volume we've been given, 3,000 cubic meters. To do this, we'll need to use the formulae for the volume and surface areas of a sphere, a cube, and a cylinder. First, the spherical balloon. The first step is to work out the radius r of the sphere from the volume v we've been given, 3,000 cubic meters, using the formula v equals 4/3 pi r cubed. Once we've got a value for r, we can put it into the formula for the surface area of a sphere, s equals 4 pi r squared. So, to find r, if the volume v equals 3,000, the equation becomes 3,000 equals 4/3 pi r cubed. Multiply both sides by 3 to give 9,000 equals 4 pi r cubed. Divide both sides by 4 pi, gives 9,000 over 4 pi equals r cubed. So r is the cube root of 9,000 over 4 pi. You'll need your scientific calculator to find this cubed root, and to get the answer, 8.947. So to the nearest centimetre, the radius r of the spherical balloon is 8.95 metres. Now we can use this value of r to find the surface area of this balloon. For a sphere of radius r, surface area is given by s equals 4 pi r squared. So if r is 8.95 metres, the surface area is 4 pi times 8.95 squared, or 1006.598. So, to the nearest square metre, the amount of material required for a spherical balloon is 1007 square metres. Next, the cube. Again, we can work out the length L of the sides of the cube from the volume we've been given, and then use that to work out the surface area of the cube. So for a cube with side L, the volume is L cubed. And the surface area is L squared, times 6, because there are 6 faces on a cube, each with area L squared. So what is the length of side L for a cubic balloon whose volume is 3,000 cubic meters? The volume V, 3000, equals L cubed. So L equals the cube root of 3000, which is 14.4225, or to the nearest centimetre, 14.42 metres. Now we can use this value of L to find the actual surface area of the cubic balloon. For a cube, the surface area S is given by S equals 6L squared. If L is 14.42, that becomes 6 times 14.42 squared, which works out as 1247.618 to 3 decimal places. So, to the nearest square metre, the amount of material needed for a cubed balloon is 1248 square metres. And now for the cylinder, which we're told is as wide as its high. That means its height is the same as its diameter, that's twice the radius. As before, we can work out the radius of the base and the height of the cylinder from the given volume, and then use that to work out its surface area. These are the two formulae we need for a cylinder. For a cylinder of radius r and height h, the volume is given by V equals pi times r squared times h. The surface area of a cylinder is the area of the curved surface, which, if opened out, is a rectangle with one side the circumference of the circular end, and the other side the cylinder's height, plus the area of the circular top and bottom. So that's S equals 2 pi RH plus 2 pi r squared. For our cylinder with radius r, that's diameter 2r, and the same height, 2r, we can find the value of r of a balloon whose volume is 3000 cubic metres. Using the volume formula, in our case the volume is 3000 and the height h is 2r, so we get 3000 equals pi r squared times 2r. So 3000 equals 2 pi r cubed. Dividing both sides by 2 pi gives r cubed equals 3000 over 2 pi, which gives r as the cube root of 3000 over 2 pi, or 7.8159. So to the nearest centimetre, the value r for the cylinder is 7.82 metres. We can then use this value of r to find the surface area of the balloon. The surface area of a cylinder is given as S equals 2 pi RH plus 2 pi r squared. In our case, the height h is twice the radius r. So S becomes 2 pi r times 2r plus 2 pi r squared, or 4 pi r squared plus 2 pi r squared, which is 6 pi r squared altogether. So, if r equals 7.82 metres, then the surface area S is 6 pi times 7.82 squared, which works out as 1152.695 square metres. So, to the nearest square metre, the amount of material needed for the cylindrical balloon is 1153 square metres. So now we can compare the results for each shape of balloon. The sphere requires 1007 square metres of material. The cube requires 1248 square metres of material, and the cylinder requires 1153 square metres of material. So the sphere is the best shape to use to make the balloon, because it uses the least material to hold the same volume. Some of you may have spotted that it wasn't necessary to actually work out the radius of the sphere or the cylinder or the length of the sides of the cube. You could directly substitute information from the volume formula into the area formula. In the case of the cube, we know that the volume V equals L cubed, so L equals the cube root of V. If we put that straight into the surface area formula for a cube, S equals 6L squared, we get S equals 6 times the cube root of V all squared. Putting in the volume we're given, 3,000 cubic metres, we can work out the value of the surface area S directly. Next, a bit of dimensional analysis. In this section, we'll look at some formulae and work out what they are for and what kind of units they are likely to be in. In the exam, it's important to get the units right as well as the calculations, so see if you can remember what all of these formulae are for. C equals 2 pi r is the circumference of a circle. A equals half the base times height is the area of a triangle. P equals 2 lots of A plus B is the perimeter of a rectangle. V equals 4/3 pi r cubed is the volume of a sphere. TSA equals 2 pi r squared plus 2 pi r L is the total surface area of a cylinder. Now, some of these formulae show the lengths of lines, such as the perimeter and the circumference. Some show areas, like the area of a triangle, and some show a volume, like the volume of a sphere. In fact, just by looking at a formula, it's possible to work out if it's a length, an area, or a volume. This is called dimensional analysis. The thing to notice is that when we work out a length, like the perimeter of a rectangle, we add up a collection of other lengths, like A plus B. No letters representing lengths are multiplied together. In an area, we do multiply two lengths, for example base times height or radius times radius, the radius squared. So with an area, two letters representing lengths are multiplied together. Remember, pi is a number, not a dimension. With a volume, we multiply three lengths together, for example length times base times height, or pi r squared times length, or 4/3 pi times radius cubed. So with a volume, three letters representing lengths are multiplied together. And again, don't forget pi is just a number. So what about the formula T equals 3b times a plus 1? If we multiply out the brackets, we have 3b times a plus 3b. So part of the formula has two letters multiplied together, so it must be the formula for an area. Do these formulae represent length, area, or volume? M must be a length, because the letters representing lengths are only added. F multiplies out to make 3a squared b plus 3abd, so this is a volume because there are three letters multiplied together. W has a squared, which is a times a, and then 2a times b. This must be an area because in both parts there are two letters multiplied together. So to summarise, lengths have no letters multiplied together, areas have two letters multiplied together, and volumes have three letters multiplied together. Not forgetting that pi is a number, not a dimension. That's the end of the section on measures and construction. That's the end of this programme about numbers and measures. There are other maths programmes about algebra and shape, space and data handling. Don't forget there are also the GCSE Bitesize books and the GCSE Bitesize website at www.bbc.co.uk/revision, where you'll also find an interactive maths test so you can quickly check what you know.
Today, someone will meet their new son, save someone's life, Mend a broken heart and kit it better. It's all in a day's work for the people of City Hospital as Matthew Kelly and Nadia Sawala return to check up on their friends. Weekdays at 10 on BBC One.
Good morning and a very warm welcome to Wednesday on BBC Two. Time to get things moving with CBeebies followed by CBBC.
Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, what's the day? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, what's the day? It's Wednesday!
I'm Poi.
I'm Sid. I'm Chris.
I'm Sue. And I'm Nicole.
And we're all here for you.
You can walk like us on a CBeebies day.
You can catch a bus on a CBeebies day.
You can play on your own.
Or have a friend to stay on this wonderful CBeebies day. It's a wonderful, wonderful, wonderful CBeebies Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday.
It's Wednesday.
Hello and welcome to the Pyjama Party right here on CBeebies on BBC Two.
Now, all week we're playing games here on CBeebies, and today we're playing a puzzle game.
We are, yes. Now, I'm going to say go. And when I say go, Nicole and I have to take these pieces of a puzzle to make up a picture of one of our CBeebies friends. Can you see who that might be? And the person who does it first will be the winner. I hope that's me. Nicole, are you ready?
Yes.
Are you steady?
Yep.
Then go. Oh, the top.
Oh, I've got an eye.
Yes, I've got the feet together. Can you see who it might be?